Hi, welcome to the Air Manager API tutorial video series. In this video we're going to be looking at some more hardware. So I think last time we looked at button LED switch and rotary encoder, so we're going to look at digital input, digital output, analog input and the PWM output. We're not going to look at analog output because there isn't any hardware that supports that at the moment, but essentially that would be very similar to a lot of these other functions. Just to say very quickly then, before we delve into the code, that pretty much all of these individual ones here, I've got the requisite add function. So in the case of digital input, hardware underscore input add, and then another function that will depend on if it's an input or an output, are ways of either reading that pin at a later stage or writing to that pin at a later stage depending on the function. So you can see for digital input there'll be a hardware input read function that you can use at some later point in your code to read the pin. Digital output will have a way of setting the state of that pin at some later point in your code. The analog input will have a way of reading the analog input at some later stage, and the PWM input, so exactly the same, a way of changing the duty cycle at some later stage in your code. So you can set the initial state on the outputs in the initial add, but the likelihood is that you're going to probably want to change it at some later point, so hence why the other functions are there as well. So let's delve into the code window. What we have here then is just a simple bit of code that will test the digital input to begin with, and then we'll get set up for the other different types of hardware, and we'll show those too. So what we have here then is there's the hardware input add function name. We've given it an ID at the very beginning, as is the norm. In this particular case, of course, because it's just a digital input, it's just a single pin, so we give it the hardware ID of that single pin. So in our case it's Arduino Uno A, and we're going to use pin D2 for this particular test. And we're going to, whenever that changes, we're going to call back the function input underscore callback. So we've created the input underscore callback function up above here, and you can see that when you do this add, whenever that pin state changes, it will call back this function and it returns the state of the pin. So that'll either be a true or a false. And then within this function, just very simply, we've got a count. We start the count off at 0 up here, and we're just going to increment the count. So every time we call this callback, we can see the count is going to change, because we're going to print that count in both of our print statements. And then just a little if statement here that basically says if the state of the input is true, so in other words, if it's a 1, the input is high, and then append the count on the end, and then else if it's obviously not high, then it must be low, so print input is low, and again append the count on the end so we can see how many times it's been called. So let's go ahead and run this now. So what you see immediately appear in the console here is the input is high. They've got pull-ups on these inputs, so the input is initially high when this gets run the very first time. And then an additional print statement here, you can see there's an additional function here where I've used a hardware input read. Now obviously we're using it straight away as the code runs here, but you could use this at some later point of in your code. But it's just to illustrate that this particular function, when you run it, the hardware input read will read whatever your hardware ID is. So your hardware input ID, which is what you've set up here, hardware input ID. So you've said for this add, that refers to this bit of hardware, the Arduino Uno A on pin D2. You're saying you want to read that particular setup with this ID, so you put that there, and you're going to return the result of that into this variable that I've named var. So and then on the very next line I'm just going to print what the state of that variable is. So in this particular case it just says it's true, which obviously stacks up with the fact that it said the input is high. It is in fact true. 1 is true, 0 is false. So that illustrates the input read quite nicely. But what we can do now is we can see that if we change the state of that pin, Let's pull up and show you what little hardware setup we've got here. So if I turn the camera on, you can see we've just got an Uno here, and I've got a wire here in the ground of the Uno, and I'm just going to ground pin D2, and you can see that as I did that, it's come up input is now low, and obviously the count has increased to 2 now because it's been around that loop twice now from its initial value of 0, and obviously if I pull that out again, there you can go, input is high. So you can see that basically all that's doing is just monitoring the state. So depending on whatever you've got in there, I've just used a wire and I'm simply grounding it, but you could have something else that's providing a 1 or a 0 input into that pin, and obviously you can read that code with these API functions. So fairly straightforward, and not much else to say really other than that. So what we'll do now is we'll get set up for the next one, and I'll be back in just a few seconds. Hi, well, we're back with the next setup for digital output. This one is again fairly straightforward, as was the digital input. What I've got set up here now on the Arduino is just an LED in the digital output pin. Now obviously digital output is not designed necessarily for driving an LED. You would use the LED function for doing that, but in this particular case we're just going to use the LED to demonstrate the state of the pin, so whether or not it's a high or it's a low. But obviously it doesn't have any of the dimming functions that you would use in terms of setting the brightness for the LED, as with the LED function. So this is merely just to indicate that you could use this as a pin as an output, as a logic high or low for something else. But an LED is an easy way to demonstrate the status of that particular line. So what we have here then is very simply the hardware output add function. We're going to use Arduino Uno A again, and this time we're utilizing pin D12, and we're going to set the initial status of that pin to false, so we shouldn't see the LED illuminate. And then just in the little timer here, you can see that we're going to utilize the other function available for digital output, which is Hardwire Output Set. So we're going to refer to the Hardwire Output ID that we created up here in the add, and we're going to change the state to true. So initially the state should be false, so the LED should be off. In other words, a 0 is written to the output pin, and then some 4 seconds later we should write a true to the output pin, which should set that pin higher. So let's go ahead and run this and see what happens there. So there we go, the initial one, the LED is off, and then we should wait 4 seconds, and there we go, the LED comes on. So not much really to see there, but just a simple demonstration of how the hardware output add and the hardware output set functions operate. Okay, I think we'll get set up for the next one, which I think is analog input. So now we have the board set up for looking at the ADC input. You can probably see here in the video that what I have got here is a little potentiometer with the 3 connections. So what I've got is I've got one of them going to the 5-volt connection, one of them going to the ground connection, and then this one here going to the analog 0 input pin. So you can see here in the code there exactly is that Arduino analog 0 input pin in our hardware ADC input add. We've obviously give it an ID at the beginning. We add the pin that we're interested in, and then the slightly additional argument that you can add in the ADC input add is some hysteresis. It is optional, so you can leave it out, but you have the option to set some hysteresis from 0 to 1. The default, as it says here, is 0.02, so that's what I've left in our example here, but this is essentially the number of the return. So in other words, if you think about that, the maximum the return could be back from this when it goes back into the ADC callback function, which is what we've created, and I'll explain up here in a minute. But that value that it returns can be anywhere from 0 to 1. So the hysteresis is essentially the same as that. So if you were to set this hysteresis, say for instance, to 0.2, that would say that the input value would have to change by 0.2, in other words 20% of the total output value, for you to see a callback actually generated. So it's, if you've got a little bit of a noisy input, or your potentiometer wants to do lots and lots of callbacks because it's seeing a bit of noise on there and it's seeing the value change like quite a bit, then you can play around with this hysteresis number and increase it. But obviously if you want to see the most realistic amount of callbacks for the smallest amount of movement, then you want to keep this number as low as possible, but obviously you don't want it being called unnecessarily. Hence I think why the default is around 0.02, so about 2% of the overall total value the input needs to change before a callback is actually generated. So that's the hysteresis, and as I said, on the end there is the name of the callback that we're going to call whenever this ADC input voltage changes by more than whatever we've set the hysteresis value to be, and in this case we've left it at the default, but I've put it in anyway in the statement just to show you where it goes in the overall function. So 2%. So our ADC callback function in this particular example gets the value that the ADC returns, and that value is from 0 to 1, so 1 being maximum and 0 being minimum. And what we've done is a little bit of maths here just to work out what the percentage of that value is out of the overall total. So we've just rounding that value once we've times it by 100, and that should give us a percentage value. And then we're just using the print statement here to actually just say the input is at whatever that percent value is, and put a little percent sign on the end. So you'll see as we rotate the potentiometer, we should get a varying amount of print statements within the console here. With exactly that statement, but with obviously the percentage of where the potentiometer is located. So you could use this analog input for, say, a dimmer input or some other control that you wanted some analog control over into Air Manager. And then just quickly down the bottom here, we're just going to use the hardware ADC input read function. And you can see we're just printing the result of that hardware ADC input read. We're using the ID that we created in the ad. So what this enables you to do is at some later point in your code, you can read that ADC input at any point. You don't necessarily have to move or change the voltage going in there, but you can read it at a later point. So if you have already read that in your statement here, and you didn't make perhaps the variable global, or you wanted to find out what it was at some later stage, you could use this statement. We're just using it in our code here, so we're just going to print it out at the very beginning. So let's preset the potentiometer somewhere around the middle. Yeah, I think so. This particular potentiometer has got a little detent position in the middle, so that should be about 50% there. So when we run our instrument here, yeah, you can see there, so instantly when we run the code here, we're not moving the potentiometer yet, but we've got a return back from this statement that says 0.5. So in other words, it returns us from 0 to 1 the value at where the potentiometer is set. And then if we move the potentiometer, you should see now the callback coming into play, and there you go, there's our last statement saying input is at so clockwise, and I'm coming back the other way now, so let me go all the way down to minimum. So the input is at 0%, and then we're going to wind it up slowly into our sort of middle location, and then all the way back up to the top. Now this particular potential, it looks like it's got a little bit of end resistance on one end of the pot, so it's only actually going up to 98%. I can't go any further with that, but depending on your hardware, it will depend on the result that you get with that. But you may be able to tailor the code to take out any inadequacies in the hardware that you're using. So that's the ADC input functions. Fairly straightforward again. Very handy if you want to read the analog position of, say, a potentiometer or some other analog input. So we're going to get set up again now for the pulse width modulation, and I've got a little servo here that I'm going to use for that, and we'll probably use a little bit of the ADC code as well, just to show you what you can do with that. Okay, so I've now set up with a little servo here to demonstrate the PWM functions. So I've got it connected onto the little headers that I've got on my Arduino board here that are for connecting sensors and the like. So they've got power and ground there and a signal pin. So I'm actually on D9 here, so essentially all it is just 5 volts ground and one of the Arduino signal pins. So because PWM is the only one that's currently you can use PWM on the Uno, that's why I'm on D9, and that's obviously this connection here with a little servo just here. So what I've got set up here then is the basic add function, the hardware add PWM add function. As I said, I'm using Arduino Uno and I'm using the D9 pin. We set up the frequency with the PWM function here. So one of the arguments is frequency, so that one there is frequency, and then the initial value that we want to set the PWM duty cycle to. So in this case 0.05, so in other words 5%. Now you can see the particular little servo that I'm using here is an SG90. From the data sheet, its frequency requirement is 50 Hertz. It is a 180 degree movement servo, and you should have to vary the duty cycle from 0.05 or 5% to 0.1 or 10%. So not a very big amount of change in duty cycle for 180 degrees, but that's what the data sheet says. What I've actually found is with this particular one, and I've got some others here as well that perform very similarly, is that the range tends to be more like 0.025 to 0.125, so more like 2.5% to about 12.5%. In terms of the full range. So I'm going to use those values because that's what gives me a nice well, approximately 180 degree movement. So there's my add. Of course I've given it an ID at the beginning. In this particular case we've called it PWM_ID, and then on the very next line we're going to change how we initially want to set our set value up, and we're going to write hardware output PWM duty cycle. So this is the way that you could use at some later point in your code, and you can see I've got some code down here. I'll explain what that does in a minute, where I'm also using the hardware output for PWM to change the duty cycle. But this is the one-off one that will get run at the very beginning, and we're going to use our ID to refer to this particular output, and we're going to say we want to set the duty cycle to 7.5%, so 0.075. So if we run that initially, what you'll see is the servo hasn't really moved because it's in the middle. So that 0.075, I've chosen it because it's sort of in the central location. So you can see I've got the lever pointing up here, roughly in that central location. So it doesn't really show you a lot or demonstrate it, but you'll see if we were to change now that value to what did I say was our minimum, 0.025. So let's change that to 0.025 and then rerun our instrument. You'll see, there we go, the servo runs all the way around one way, and then we'll change it to our maximum, which is our 12.5% duty cycle, which is 0.125, and then there you go, it runs all the way up about 180 degrees in the opposite direction. So that's the 180 degrees of travel. We'll change it back to our 0.75 position. There we go. And then what I've set up here is just a little example of how you can move your servo depending on some other data. So essentially what I've got is a little function here where I've created this function called move servo, and I've said that you need to give it a value, and then in here I basically work out what the new duty cycle needs to be based on the range that I'd worked out previously for the servo here, and I take that value and I do a bit of maths there and I apply a new value. So I use the PWM duty cycle output function to write that new value to the PWM output pin. So what that should mean is, depending on whatever this value input going into this move servo function is going to be, the servo should position itself accordingly to the value. So now where do we get that value from? Well, what I've done is I've left the code in. You can see I've still got in the camera view here, I've still left the potentiometer here and left it connected to the Arduino when we looked at the ADC input. So we're going to utilize that. See, the function name is move servo. If we come up to where our ADC code was that we looked at previously, you can see now I've added a call in here that calls the function move servo with a value, and the value is this ADC value, so it's from 0 to 1. So if I uncomment that now, what we should see is when we run the instrument, the servo should move with the potentiometer. So the potentiometer is in the middle at the moment, so that's why the servo's in the middle. But if I were to move it to its minimum position, you can just see as I'm turning the potentiometer now, the servo's moving with it back to the middle position and then round to the maximum again. So you can see I can move the potentiometer backwards and forwards, and the servo will move accordingly based on the position. So a little bit of feedback there from the potentiometer and then back out to the servo. So just a way of demonstrating that you can take one input and obviously feed it out to another to provide some movement of the servo though. So this is only a cheap SG90 servo, but similar would apply no matter what servo. You just need to do a bit of research on what your total range of travel is, and obviously what duty cycle is required to be output on that PWM output to achieve those particular movements of that servo that you have. So I think that concludes this video on this hardware segment of the particular functions that we've covered. They are digital input, digital output, the ADC input, and the PWM output. Thanks for watching. Join me again soon. Thanks. Bye.